I'm Reginald Frank, and I'm here to present Picsou, which is joint work between UC Berkeley, the University of Oregon, and the University of Michigan. And in this talk, I want to convince you that replicated state machines need to support efficient and reliable communication, and that we can solve this need with our new system, Picsou. Fundamentally, all distributed systems need to handle machine failures, and they do this by using replicated state machines, RSMs for short, as a failure handling core. RSMs replicate work across multiple machines, giving them the ability to support reliable storage and compute despite machine failures. Key value stores use these properties to store and update key value pairs. Databases like CockroachDB and Spanner use RSMs to execute transactions and store the results. Even machine learning infrastructure like Hugging Face use RSMs to keep track of model weights and versions. But these systems do not live in isolation. There are many situations where replicated state machines must communicate. Take cross-organization collaboration, for example. Our group has talked with government agencies and found that for operational sovereignty, services cannot be managed across agency borders. This means that every agency is forced to manage their own data by running their own key value stores or databases. One might use etcd, while another might use TiKV. And then any information shared between the organizations must be communicated across the two key value stores and then explicitly reconciled. We also see this same pattern in industry, where separate teams and services will interact but may manage their data separately for simplicity. Even inside of one organization, there are still numerous situations where a team may want disaster recovery for their databases or key value stores. One way of accomplishing this is by having a system deployed in one data center back up its local state into another data center. We also see cross-RSM communication in financial blockchains, where users often want to transfer money between different blockchain providers using a protocol called the blockchain bridge. While cross-organization collaboration, disaster recovery, and blockchain bridges are all very different applications, they all share the same core idea. Replicated state machines are connected, and they need effective mechanisms for communicating between each other. The problem, though, is that today, there is no formal, scalable way for RSMs to communicate. We find that existing solutions are ad hoc, have vague guarantees, are inefficient, or rely on trusted third parties. So with this work, we wanted to start from the ground up and answer a fundamental question. What are the necessary properties of a protocol that allows replicated state machines to communicate? To concretize this, we set out some requirements. First, there should be a precise and formal way to discuss RSM to RSM communication. Applications need to know what a communication layer is providing them with. Second, in the common case, we should also have low overhead. And the implementation needs to be robust under failures. Actively crashed or malicious nodes should neither affect correctness nor cause the system throughput to disproportionately drop. The solution should also be general. Arbitrary RSMs with heterogeneous sizes, communication, or fault models should be able to reliably communicate. And finally, we should be able to do all of this without relying on a trusted third party to handle the communication for us. And I'm going to take the next 10 minutes to convince you that it's possible to satisfy all 5 of these requirements at once. To address the first bullet point, we introduce our new primitive, the cross-cluster consistent broadcast, C3B for short, which formalizes what it means for arbitrary RSMs to communicate. Next, we introduce Picsou, our new system which implements C3B, satisfying all of the design requirements that you see here. Also, for those of you who don't know, Picsou is the French name for Scrooge McDuck. Just like Mr. McDuck likes to save money, our system Picsou likes to save bandwidth. But before we tell you more about our system, let's first do some review on how replicated state machines work. Replicated state machines are designed to handle failure. In an RSM of n nodes, in this case, 3 nodes, we say that only up to f machines can fail. In this case, only 1 machine. The RSM, though, does not know which machine will fail. It only guarantees that it can handle up to f failures in total. If a machine will eventually fail we call that machine faulty. Otherwise, we call the machine correct. Importantly, a correct machine will never fail. And these are just standard RSM definitions. There's nothing new here. Crash fault tolerant replicated state machines then handle crash failures, where a failed node can no longer send or receive messages in the protocol. While Byzantine fault tolerant protocols can handle malicious nodes, think machine compromises, where a faulty node may send invalid or malicious messages in the protocol. In both of these cases, though, replicated state machines can handle the failure because, as planned, only F nodes failed. As an aside, for those of you who are very familiar with replicated state machines, you would need 4 machines for the second example. But let's move on and see how this background information informs what communication between replicated state machines will look like. At a high level, what we want to do is simple. If I have my 2 key value stores, I want to enable the ability for them to exchange messages with each other. etcd should be able to transmit a key value pair and know that it will be reliably delivered at tie KV. And this should be able to happen in both directions. But remember, under the hood, both etcd and tie KV are replicated state machines where nodes at any point may fail. So to ensure that messages are handled reliably despite this, we introduce our new logical primitive, the cross-cluster consistent broadcast. And this primitive formally defines what it means for messages to be reliably transmitted and delivered by replicated state machines. Additionally, it also imposes correctness conditions on what happens to messages that are passed through the protocol. In this talk, though, we will just focus on what it means for a message to be delivered. As we covered in the overview, we cannot rely on faulty nodes to send or receive messages. Therefore, our definition only treats a message as reliably delivered if a correct node in the receiving RSM outputs the message. For this talk, that's all you'll need to know about C3B, but please check out the paper for more details. Now, going back to our prior example, this means that sending a message between the 2 clusters is actually not sufficient. Even if a node in tie KV receives a message, it will mean nothing if the node fails before it can do anything with the data. To guarantee that a message was reliably delivered, we need a correct machine to receive the message. The key challenge in accomplishing this, though, is that our protocol needs to effectively deliver messages to correct nodes, even though it can't tell which nodes are correct. To see how we approach this, let's take a brief look at our protocol. Starting simple, let's consider the situation where we have 2 nodes which want to communicate. In general, our protocol supports bidirectional communication, but in this presentation, we will only show how to send messages from the blue cluster on the left to the orange cluster on the right. For this, the blue node can begin by sending over a message. And we can send over multiple messages before hearing back a response. Then after the orange node processes these messages, it can respond with a cumulative acknowledgement representing everything it's heard so far. After receiving the acknowledgement, the blue node now can be certain that the orange node has received its message. This process of using cumulative acknowledgements for message delivery is the exact same as TCP. And this works great for one-to-one communication, but in general, we will need to connect multiple nodes to multiple nodes. So here we have a more realistic example, where we have 2 RSMs, each composed of 3 nodes, where 1 node might fail in each cluster. And let's just try to generalize our old approach. All the blue nodes are in the same RSM, which means they all have the same access to the stream of messages that need to be sent to the orange nodes. This means we can have each replica send messages in parallel, increasing our throughput using round-robin scheduling. Once the messages have been received at the other network, they can then internally broadcast the messages, and this lets us disseminate information across the entire receiving cluster. Finally, the opposing network can send back their acknowledgements. And it seems like we're good. We sent across 3 messages, and all nodes heard back ACK3. But before we celebrate, let's focus on the perspective of a single node. This replica has only heard 1 acknowledgement. And this could be from a faulty node, which immediately crashes after sending the acknowledgement, or even worse, it could be from a malicious node, which is completely lying about what messages it's received. If we take a step back, there's 2 things which we are missing. First, the blue cluster needs a way to detect that its messages have been reliably delivered, namely, that a correct node has heard of messages 1 through 3. And second, remembering our efficiency requirements, we want to somehow learn this information without sending additional messages. To solve the first problem of detecting reliable delivery, we introduced the concept of a quorum acknowledgement, or Quack for short. The idea with Quacks is simple. If F nodes can fail, then F responses alone is not enough. Instead, if we received F plus 1 replies, then we would know that after F machines fail, there will be at least one node with the message, regardless of which machine fails. This solves our robustness problem, but quorums fundamentally are group communication. And that seems to inherently contradict our efficiency requirement of not sending duplicate messages. So let's see how we get around this. Our key insight is that while we do want group communication, we don't need to do it all at once. Our example so far finished with a node receiving acknowledgement for messages 1 through 3. This single acknowledgement does not form a quorum, so our node is not sure if the message has been reliably delivered. And the same is true of the other 2 nodes in our system. But if we continue our example, the blue cluster has more data to send. So we'll pass this across the network, and the orange nodes will broadcast this data internally. Now, the orange nodes have a new acknowledgement to pass back to the blue network. But this time, we'll have the orange nodes rotate receivers. So now our node from before has just heard new information. One node has received all messages up to 4, and if we combine this with our previous message, we'll find that this node has actually heard a full quorum of 2 machines which agree that all messages up to 3 have been delivered. And this lets us form a quack for all messages 1 through 3. Asynchronously, the other 2 machines will form quacks as well. And this process is at the core of how our protocol remains efficient and robust. Just by rotating receivers and counting acknowledgements, we can generate quacks for free. And this lets every node determine whether a message has been delivered or delayed, which enables us to efficiently resend message only when required, providing us with good performance both with and without failures. Now, I've shown you how Picsou schedules messages in the good case, and also how we use Quacks to track message delivery. Our full paper also covers how we can extend Quacks to track multiple dropped messages in parallel, allowing us to speed up message retransmission. And then we also dive deep into how we handle proof-of-stake systems. To get you curious, our solution ended up citing Alexander Hamilton, which is something I never thought I'd do in a CS paper. I encourage all of you to go check it out. But now, let's see how our design translates into performance. To ground our results, we compared Picsou against a variety of other strategies which send messages between replicated state machines. First, leader to leader will have replicated state machine leaders send each other messages followed up by an internal broadcast. GOBFT contains a similar strategy, but leaders will effectively directly broadcast sufficient data to the opposing cluster. All-to-all is a naive strategy where every node will broadcast every message to the opposing cluster. And we also tested against Kafka, where each node will send messages to its own partition, and receivers will download all committed Kafka transactions. In our full paper, we have a wide range of tests, but here we'll just focus on the maximum throughput of each strategy. To test this, we deployed various size systems in the same data center and kept track of how many pre-computed 1 megabyte messages each strategy could send per second. This graph shows this, where the x-axis holds the network size, and the y-axis shows the throughput. Our results then showed us that leader-to-leader, GOBFT, and all-to-all have nearly identical performance. This is because these strategies do not attempt to shard the stream of messages across separate nodes. This means that the maximum performance of these strategies is bottlenecked by the maximum speed of a single node, and that bottleneck gets worse as the network size increases. Unlike our other strategies, Kafka runs consensus and persists operations on the critical path of transmitting messages, which appears to limit its performance. And then Picsou because it can safely shard messages across all nodes, can achieve higher performance than the other strategies tested. As the network grows larger, the number of senders we can leverage grows as well, which enables us to scale to larger networks. So overall, today I hope I've convinced you that many applications rely on cross-replicated state machine communication. We can formulate this problem using the cross-cluster consistent broadcast, and Picsou is able to reliably and efficiently deliver messages between replicated state machines. Thanks.